Okay, see if I can get this. All right, so we'll talk about PowerPollen. It's a technology that we've developed. Our company is about increasing ag productivity first. Our goal is to do that by improving the seed, and a lot of that is about enabling hybrids. And the what, more precisely of what we're doing, we're enabling more effective cross-pollination. So as you think about cross-pollination, why does that matter? It matters because it always leads to higher productivity. I imagine many of you are already well aware of this, but if you look at the 4 major crops of the world, and you see 2 that have about 4 times the productivity as the other 2, sorry. I better shut that off. All right. Corn and rice, which both can be crossed cost effectively and can make hybrids. That led to higher productivity, better breeding methods, and ultimately the wheat and soybean crop, which cannot be cost effectively crossed at the moment. There are many people working on that, has much lower productivity as a result. So let's talk about what the problem is. And as an entrepreneur that I've been for the last 3 years, first thing you have to tell investors is what the problem is. The problem is that enabling cross-pollination is difficult and expensive, and in many cases it's cost prohibitive, as in wheat and soybeans. So the solution we're proposing is to deliver desired viable pollen, and that's part of the problem, is grass pollens die very quickly, to the right location at the right time while avoiding undesirable contaminant pollen. So I'll go into a little bit exactly what I mean by that, but we'll start by talking about corn and what a seed production field looks like versus grain. So this is the seed company's manufacturing process here. Basically what you see is let me get my pointer. There are strips of kind of a darker green, which represent the females. There's, in this case, 4 rows of those for every 2 that are males. And the female rows are detasseled. There's a little pink dot right there, and there's a few others through here. Are humans, migrant workers out there plucking tassels out of the female rows, and then you let Mother Nature do its part. So this is the production process. The problem with it is this. If you look up close, it takes a lot of people. It's very labor intensive. And the fact is, this process hasn't changed in almost 100 years, since the 1920s. So what is the exact problem with it? First off, because it relies on the wind dissemination of pollen and the way it's set up, you get poor pollinations that lead to more than 20% seed yield loss. You get a high contamination and discard rate compared to other industries. This is pretty high, about 7%, and very high labor and resource costs, as you could tell from those pictures. So our solution, jump right to that, and then I'll explain how it works and give some examples. We call it PowerPollen versus the traditional almost 100-year-old method. This is a direct comparison of the two. Focus first on pollen timing and delivery. With PowerPollen, because we use preserved pollen that we can deliver mechanically when it's needed, where it's needed, we can improve the pollinations, and it's a weather resilient process where the traditional system relies on about a 3-hour window, 3 or 4 days in a row, and can be hampered by the weather and results in poorer pollinations than are ideal. And as a result of this on-demand and weather-resilient method, you can decrease some of the very expensive processes like field isolation, detasseling, and male presence. Those are expensive parts of producing corn seed. And you can also increase yield on average about 20% from 70 saleable units. That's supposed to say 85. There's a little deletion there. Sorry about that. So how does it actually work? We take advantage of the fact that corn makes much more pollen than it needs, and it dies very quickly, so we take a very small part of that. We preserve it. We've shown now that we can preserve corn pollen for about 8 months, and that's a first in the corn industry to be done at scale. And we take that pollen, that small amount of pollen, we direct it where it's needed, when it's needed, which are the silks on the ear, the developing ear, and so you need much less pollen than the traditional system. And as a result of this, because you can apply pollen at more ideal times, you can essentially preempt contamination. So when you apply pollen in the early morning hours, You make a pollination to the silks that were growing all night, and they're waiting for pollen to show up at around 9 a.m. when the natural pollen shows up. And a silk that is pollinated is no longer at threat for contamination. So the expensive contamination avoiding measures like detasseling can be reduced as a result. And then you also see an increase in seed yield. So what does this actually look like? We've started to mechanize this. We have the collection mechanized. This is an actual high clearance vehicle called a Hagee, in which we have mounted 4 pollen collectors onto this, and we can collect pollen in mass very quickly. It's not a rate limiting step for what we do. This is an actual production field. We take it through a conditioning and preservation and storage process, and this is the output of the Amphasys machine, like the one sitting over here, that allows us to monitor the health of that pollen while it's in storage. I'll talk a lot more about this. And then we will dispense the pollen in a scaled way. This is just a public picture of what we expect it to look like. We don't have that fully mechanized yet. We plan to have that mechanized by this next summer. It was semi-mechanized where people could go through the field with guns and shoot pollen and make pollinations this last summer. Yeah.
Everybody wants drones.
So could drones do it? Yeah, we've thought about drones. If you have enough pollen, you sure could. But you can't get as precise with a drone, at least right now. But we're definitely considering drones. We own a drone. How about that? All right. So good question. Yeah, and by the way, interrupt anytime. I'm happy to answer questions as we go. So how it works. Let's talk about collecting pollen first. These are the collectors we used last summer. They have large Tupperware reservoirs on the bottom of these. This next summer we plan to have those connected into a central storage unit on the machine. This last summer, this is what we used. You get a lot of pollen from this, and it doesn't take much pollen to pollinate. If you do it right, around 50 milliliters could pollinate an acre, 50 milliliters or less, if it's done right. 25 milliliters theoretically. And we automatically, right when we harvest this, the most important thing is that you start with high quality pollen. So we take a small subsample. We have a unit in the field on site, one of the Amphasys units exactly like this one, and we quickly take a measurement. And the beauty is it's an instant measurement as far as we're concerned. I know it takes a minute or two. We consider it instant. And before we even have all our pollen conditioned and into the conditioning facility, we already know if we had good pollen to start with, which is a very important piece of this. So we confirm that the fresh pollen we've collected is high quality. Next, talk about the preservation. First, I'll back up a little and explain why the Amphasys machine was important for method development for us. It provided instant feedback, as I said, and the other methods of doing this are through germination media, and you look at the tubes. That works. It can take a little while, it can be inconsistent, and it's a fairly conservative measure, but it does work. The other way is to actually pollinate an ear and then look for kernels some days after you pollinate. So that's a fairly long process. This is instant. Within a minute or two, you have your results. And the beauty is that the iterations of an experiment, getting results, making decisions, and refining the experiment can be very quick. So we have experiments involving freezing and other treatments that only take a few hours. And so if you get instant feedback, you can actually run an iteration of that all within one day. It's very nice. It's enabled a lot. And so we take very small amounts of pollen, we put them in ampules, and we subject those to very small microclimates and controlled environments where we just alter humidity, temperature, and other things to determine the effect on the pollen. And this Amphasys work has helped us get results very quick and develop 2 primary methods. One that's short-term for corn, which means if you want the pollen in less than 30 days, you use that protocol, and one that's long-term. If you want pollen to be older, you want it to store for more than 30 days and up to 6 to 8 months and counting, you use the other method, okay? And then at mass, preservation and storage in mass in the mechanized system, we have large conditioning storage methods which can store enough pollen really for thousands of acres. But for this next year, we're talking about mobile units that store enough pollen for hundreds of acres. And we're looking at applying pollen to about 2,000 acres this next summer. Yeah?
Is there a reason you would think this would not work for other plants?
So,
Be able to store them for months?
So we believe that for the grasses, this should work with some optimization, the method that we're using. Yeah. Now for many crops like trees, I think we have some olive pollen over here. It's sitting on the table. It's alive for weeks without doing much of anything. But for the grasses, we believe that what we've learned we could apply to any grass. Yes. Good question. So when we put something in storage, just like seed in storage, you have to occasionally sample that. And so the Amphasys unit also allows us to do that, get quick feedback, make adjustments if we need to. And in our preservation and storage, we also plan to have automated humidity measurements and pollen moisture content measurements, which we can then adjust the environment to get the pollen exactly the environment we want, to keep it alive and healthy for very long periods of times. Yeah?
With the corn going out, and since you're measuring with the instrument over time, are you ground truthing also to validate that the instrument is actually correctly saying that it still is viable to pollinate?
Yeah. So are we ground truthing with actual data from, in our case, we've done that with actual data from pollinated ears to confirm that pollinations match the data from Amphasys, and it's a pretty good correlation, a very good correlation, that we're comfortable moving forward with just the Amphasys data in most cases. We do in the fields this summer and in the past, we still will make live pollinations. We have a protocol for that where we have a shoot-bagged ear, we'll make a pollination, not for every sample, but for a certain subset of the samples to confirm. And so we always have confirming data through the season. So it's a good question. And the interesting thing is, though, when you're pollinating to an ear, it depends on how much pollen you put on. So you have to meter it. It's not as easy as just make a pollination, because usually people who make a pollination put way too much pollen on. So you have to meter the pollination to get a good correlation. Yeah. Was there any other? Did I see another question? Okay. So we sample this at several time points during storage, depending on what we need it for, how long we need it, and what the actual application is for. And then finally, dispensing the pollen. It's critical that when we go to dispense, that we take a micro subsample right before dispensing, and we take the rest of the pollen out to the dispensers, and we know even before we load the pollen onto the dispensers that the pollen is alive. And this has been there's no other way to do this. Germination media wouldn't tell you. We want to know before we're running through the field that it's alive. And we get that data. It's been a tremendous help for our program. And so let's get to some data. We've had 3 seasons of results to show that indeed we are increasing seed yields by more than 20%. And I'll show you data from last summer that averages much more than that. We've cut the discard rate by more than 50% because of less contamination. And we've increased the pollen viability by more than 5,000 times. In other words, we're out to 8 months where it's usually 1 hour. We've gotten out to about 8 months, so about 5,000-fold the lifespan. So this is an example in the field this last summer in which we were able to use in-season adjustments to mitigate the effect of drought. So when water stress occurs, what the corn plant does is it puts less resources into the female, and the female gets delayed relative to the male because it takes less energy to make pollen. And so what happened in this field is we were standing out there on the 20th looking at this field, and it was evident that the peak pollen had occurred on July 16th, about 3 or 4 days before this. There were very few silks out yet. So this is the natural pollination that occurred. It's a little better than this on average. I'll show you on the next slide. But this is just an example ear that we harvested at 14 days after pollination. It looks very poor. We came in 3 days later, 3 to 4 days after we were out there, and about 6 to 7 days after the peak pollination. And we applied about 3-day-old pollen, and you can see how we filled in the missing silks that were not caught by the natural pollination. And the neat thing about this immature ear, you can see those open pollinated kernels that were just like these over on this ear. And you can see how we fill in the gaps with the smaller kernels that are 3 to 4 days behind the larger kernels. They did catch up. I'll show that on the next slide. But the big eureka moment for us was that a single pollen application could bring back all of the yield that was lost. because of the water stress and the missed nick in this picture. So this are those same subsampled ears out of the same field, and this is the average, very representative sample. You can see a lot of variation in the conventional open pollinated system, and our system, in which we were able to show that we tripled the seed number, and in addition to that, the kernel sizes in these are much better than the kernel size in these poorly pollinated ears. These kernels are much bigger and they're less valuable to the farmer. So this was a seed limited in-demand product, this particular field, where they could have sold every kernel that they produced. It's worth about $200 per unit retail, actually a bit more than that. We were able to add about 50 units to this field of production. At $200 a unit, the average value for this example would be about $10,000 per acre.
So if you're looking at drought effects, are you guys trying to do natural storm coming in water, or is this overhead water? Or?
So in many production fields, seed companies like to irrigate, but the smaller ones irrigate probably a third or less. And this was one of the smaller companies. And so we were focusing on fields that were not irrigated. We weren't expecting water stress. And in fact, for the last several years, it wasn't since 2012 and 13, we've had plenty of water every year. So 17 in southern Iowa, there was a lot of water stress. So we just took advantage of the fact we found this field where there were problems. Can we rescue this field? Yeah, it's pretty obvious that we could. Now these are small plots. We didn't have this fully mechanized, but it's a pretty vivid example. We were in 4 different fields. The top field is the 5002 field, where we tripled the kernel number compared to control. There was another field nearby that had similar problems, where we increased the kernel number by 90%. And then the other 2, both of which did not have water stress, we increased by 8% and 17%. But knowing what we know now, if we went back and did it, our improved methods, we would easily hit 15 to 20% increase in this third field here, 548, and over 30% in this fourth one. We've learned a lot. We actually about a third of the silks were missed in this field because of a moderately poor nick, and we only brought back about a fifth of them. We didn't bring back a whole lot, but with what we learned from this last summer, we believe next summer, if we had a similar situation, we'd increase it by at least 30%. So a big question for us, this is all talking about seed. So I want to shift just a little bit. What about grain? Could better pollinations, and in particular cross-pollination, improve grain yields? And you may think that it's obvious. The answer is yes, but it's not actually obvious that would occur. I'll explain. We are going for that in corn, which is the most productive crop. You asked about other crops. We also are interested in wheat and rice. Wheat's the most widely grown crop, most hectares. Rice is the most valuable crop. We think that PowerPollen has applications in all 3. So we're focusing on seed, but I wanted to talk a little bit for this crowd about the next application. So let's talk about corn grain in particular. The same preemption used for seed could be used for grain. There's an article in 1990, and there's been several since then. This one's in Crop Science, where it was shown that if you could cross-pollinate a cornfield, now we're talking about a farmer's field now, not seed production, you could increase seed yields as high as 20%, and which was a surprise, I think, to most researchers, that because it's self-pollinating, you're getting inbreeding depression right away. Really, there's literature out there since the 20s that show that cross-pollination is always better. You get increased hybrid vigor in that field. And the problem is that we grow monocultures, most farmers, so they self-pollinate. Our internal research has shown similar results. So the problem is that grain producers start with hybrids, very expensive, $250 a unit, but they plant them so that they self-pollinate, and then you get a reduction in yield as a result. I haven't found a farmer yet that's aware that this is happening, but it's in the literature, it's happening, it's real. So what could you do to increase that? This is what we're proposing. We haven't done it. We've done it on a very small scale, but imagine you had a service provider for PowerPollen, And these green ovals are farmers' fields. You map out the earliest flowering fields, and you determine relatedness of hybrids out there in the countryside. And you likely have some kind of software that would do this for you, would quickly determine which fields to pollinate, to carry pollen to the next field, and basically swap pollen between fields. The technology we're developing should be able to do that, and you basically just move pollen from one field to the other. You may just swap two fields with each other if they're pollinating at the right time, but if they're not, you preserve it and come back and apply it. This is where drones would apply, because there's so much pollen, you could collect so much, you could just broadcast it from one field to the next. So this we're pretty excited about. Trade pollen between fields, avoid self-pollination, increase grain yields 5 to 15%. We're showing numbers without very good sources of pollen. We don't have elite genetics for our pollen, but we're showing increases in the 5 to 10% range, and we're confident we could get well beyond that if we select for better pollinators. And again, all along the way, you would have to monitor your pollen viability with Amphasys. Okay? Now, if you combine this with male sterility, you could get another yield bump. If your hybrid's male sterile, it yields more if you can pollinate it. So there's other things you can do to increase yield in this kind of a situation. So can better cross-pollination improve wheat and rice seed and grain yields? We definitely believe that the seed yields can be increased. We know from data that rice hybrid seed production sets about 50% of the seed that it has the potential for. So you could double the seed yield. Grain yield is another question. If you could cross-pollinate wheat in a grain field, would you increase the yield? We don't know the answer. It's to be determined. Same for rice. It's much harder to think about cross-pollination in a production field for rice, for grain and wheat. Okay. But we think it's possible. We think that's kind of the vision down the road for this technology. There's a bunch more applications, some that Carolyn will review, but a lot on the breeding side of pollen, enabling wide crosses. Right now, in seed production, a seed company doesn't want crosses any more than beyond 2 weeks, about, give or take. This would enable crosses that go 4 weeks or longer. Every inbred or variety you use could be used as a male, even if it's a very poor male. We can enhance the production enough that it could be used as a male. You could have new breeding programs to maximize that we call it a xenia effect in grain fields, where you get cross-pollination. And there's a lot of other related applications as well. So with that, I'm going to shift gears, put the problem back up and the solution, but shift gears to have Carolyn Huber come up and continue with the discussion. Any questions? Yeah.
I understood the question. So have you received any comments from the large industry, whether they're in favor of or against this technology?
Yeah, I think all I can say is in general, everyone likes that we're solving a 90-year-old production method that needs to be improved. We've talked to many seed companies. We haven't had anyone say it's a bad idea or come up with a reason why you shouldn't do this. If you can scale it and get it to work, and key is if you can preserve pollen. Yeah.
Well, maybe you're going to talk about this coming up, but in the Amphasys machine there, how does the output of that compare to just something like tetrasolium activity staining or something to test pollen viability?
I'm going to refer that to you guys to answer. Yeah. Any other last questions for me? Yeah.
You were positing that you could not only use this for like seed production, but also for actual grain production. If that's true, do you have an estimate of what the cost per acre would be to collect and then disperse? And is that consistent with, even if you're just looking at a 10%-ish yield increase? Does that leave a good ROI to the farmer potentially?
Yeah. So the first question was, are we positive it will work for grain? I think that's what you asked, right? And
I said not positive, but I said positive. So like hypothesis.
Sorry. Yes. Okay. So talk about ROI. So at $3 corn and 5% yield increases, absolutely not. We probably can't get cheap enough per acre to do that for the grain farmer. But at $4 corn and above, we probably could do 5%. So it's kind of you got to think about both pieces. If it's 10% yield at $3.50 corn, it would probably be economical. We think the price has to get down to somewhere between $30 and $50 per acre to have a good ROI. Have maybe a return of $100 to $150 per acre, and minus costs of about, say, $35. It would be a good production decision to apply the pollen. Yeah, and then there are other applications where you have drought stress where you could increase yield tremendously. But for the average situation, that's about how it comes out.
One related question on that: have you modeled, potentially doing some sort of a top cross, where you would have a specialty pollen that would, potentially allow you to get a desirable trait that would be accessible that way?
Well, I'll just say I used to be a high oil top cross breeder, so absolutely, that's about all I'll say.
That to me actually seems pretty exciting.
Yep. Right. So you could modify your crop up until the time of pollination, decide what you want. Right. You could pick your trait as long as you can get it in pollen.
How much pollen can you get per acre? And can you, if you needed to just produce a boatload of top cross pollen, is that cost effective?
It could be. If it's high oil, you can get boatloads of pollen from giant tasseled parents. Yeah. But it depends on what it is, definitely. And if it's something that is already in the countryside, you could probably go get it. But that's a good question. There's a question right behind you, I think.
You talked a lot about corn and other crops. Hybrids are often relying on restorers, fertility restoration. So you could potentially do without a fertility restoration and have a sterile
Right.
hybrid, right?
Right. Exactly right. So yep.
So have you tried it another crop
No.
like sorghum or?
Only corn. And we're planning to test a sterile hybrid where we bring pollen in to see if we get a double hit. You get the hybrid vigor plus the sterility kick. Yep. It's good observation.
Well, this scaled down, let's say you want to make a cross of something that's clinic adapted and you want to save pollen just to make a breeding cross. Let's scale down.
So you want to finish the last part there again? I didn't quite catch all of that.
You want to save pollen from something that's unadapted and
Ah.
use it to make breeding crosses. Can you scale down a very small scale?
Yes, absolutely. In fact, we started small, so there's no problem with that at all. In fact, you could talk to Mark Westgate as well, definitely. In fact, we're thinking about making kits for research level. I was just talking to Jean-Pierre somewhere in here about that. So definitely, that's a possibility. We don't have it yet, but it can be done. Yeah. Okay, we better keep moving.
Yeah. For the sake of time, we'll continue. Thank you very much, Todd. I think it was a pretty intriguing life example of what their company is doing. I think you're going to hear from Caroline now some other applications and other examples of industry usages for the technology. So I'm going to call Caroline here. She's a director of business development for Amphasys from Switzerland. She has graduated 2 master's degree in biotechnology and water treatment from the University ETH in Zurich, and has an MBA. She's been working with leading companies like Tican, Quiogen, Life Technologies, and now I'm happy she's with us in different product management roles, and she brings an extensive international marketing management and laboratory automation in genomics. So thank you for...
Thanks, Ronan. Thanks, Todd. Just need to